short, but we're going to split into two topics essentially. Number one will be on kind of a general idea of why photovoltaics are important and where things are going, and where, and also a little bit of a historical appreciation of where we came from. The second part of the talk, I want to delve a little bit into the physics, particularly the semiconductor physics, and also talk briefly about some of the new ideas that are being developed, not only here at the University of Utah, but also elsewhere as well. So, much of these slides are courtesy of Rujun Sun, who was a postdoc in Mike Scarpulla's group in Material Science Department, but currently she's a professor at a university in China, Dennis Pruzan, and of course Mike Scarpulla and others as well. So what are photovoltaics? This is what we want to kind of go over. Where are they used? Why do we want to use photovoltaics? What is the current status of PV and where things are going, which is, of course, of great interest, both globally, but also locally in Utah. And then, of course, the second half, we want to talk a bit more about how do solar cells work? How do we measure quality efficiency? And we talked a little bit about this last class. As I emphasized before, this is actually quite important. So it's really critical for us to understand, if we come up with new technologies, how do we actually qualify them? What types of solar cells are out there? What kind of engineering went into making some of these champion devices? This is very, very interesting and very exciting area. It's changing almost every day. So it's an extremely exciting area to work in. Also, I should add to this is a very timely that we are having this lecture today because, of course, there's the economic summit on renewables happening this week in Glasgow, as many of you who follow the news probably aware of. These topics we're talking about are extremely critical and important for the future of our planet. So what are photovoltaics? Essentially, what we are talking about is a type of energy conversion. As we talked about, it's a type of heat engine. So it's a form of energy conversion going from solar radiation from the sun, being converted into AC power that you can plug into the grid, or you can use to power your car. Actually, the cars typically use DC, but AC power outlet in your houses where you can plug in appliances and so on. How does this happen? There are many steps here. The most important, well, all of them are equally important, so I shouldn't say most important, but the first step is a conversion of the photons from the sun into electrons. So that's what's done, what happens with the solar panels. The sunlight comes in, there's a photoelectric effect, which, by the way, was the explanation of the photoelectric effect was the reason that Albert Einstein won the Nobel Prize. It is nothing to do with relativity, interestingly. So that's an interesting anecdote. In any case, the photovoltaic panels convert the photons into current, electric current, and the current then goes through a few different subsystems, something called a charge controller, which essentially tries to manage the current. In other words, if you have huge fluctuations, you have a way to essentially kind of balance that out, a bit like a load balancer. And then it goes through a battery system, not always, but often, so which is used to charge the battery. Sometimes, of course, you don't have the batteries. This is directly converted, sent to the inverter. The inverter, of course, photovoltaic panels produce direct current. So what's the difference between direct current and alternating current? So for those of you who are not electrical engineers, you may not be familiar with these terms, but this AC refers to alternating current, and DC refers to, of course, direct current. Now, what's the difference? Direct current is the current is only flowing in one direction, so it's always positive. On the positive axis, this is time, this is current. Alternating current can change direction. So you basically have something which goes up and down. Now, there's a historical reason, and I won't go into the details. There's a historical reason our grid is based on alternating current as opposed to direct current, although there are some arguments that direct current is more efficient in terms of transmission. But that's a topic outside my area of expertise, but those in the power engineering actually discuss these things. But all our grid is currently based on alternating current. In other words, the current can be flowing in both directions. What does that mean? So what that means is if I have a battery here and I have a load here, like my light bulb, the current is flowing in both directions. And of course, in a light bulb, for instance, the direction of the current is not important, right? The light bulb simply works by passing a current through a resistor, and it doesn't matter which direction the current is flowing, it'll work either way. Now, it is important that the solar panels create direct current. The current only flows in one direction, as we will see shortly. However, our homes, the outlets in our homes expect AC current. So that conversion from a direct current to an alternating current needs to happen. And that happens via something called the inverter. Okay, this is a very, very important aspect of solar panels. In fact, I would even argue that these two things are the key bottlenecks in adoption of solar panels today. Solar panels themselves are actually dramatically reduced in price, but the inverter and the batteries have not. So these are really the key innovations that are waiting to happen. Inverter has other issues because it actually, the solar panels can last more than 25 years. In fact, if you go purchase something, this is the warranty that they'll provide to you. However, the inverter typically has a warranty about 7 to 8 years. Sometimes it's a little higher. So obviously the inverter needs to be replaced before the solar panel stops working. Or, there are solar panels which have gone more than 40 years because, so these can actually work for a very, very long time. Something to keep in mind. And we'll talk a little more about the balance of systems cost later. But in any case, it is the direct conversion of light to electricity that happens within the solar panel. And it's essentially a giant semiconductor diode. In fact, I wouldn't really call it a giant semiconductor diode, but it's a series of semiconductor diodes. For those of you who know what a diode is, it's basically you have a resistor. And we'll look at this in a little more detail. But essentially, a solar panel can be modeled as something like this. A series of diodes with resistors. Okay. In fact, we will look at the model more carefully later on, but this is a reasonable approximation of what to expect. Now, the diodes are, of course, reverse biased. In other words, the current is always flowing in the opposite direction, which is an interesting aspect of this. We'll come back to that later. Okay, with that basic understanding, let's move on and try to think a little bit more closely about why these things are important. Now, here's an interesting plot of the energy consumption by the source. And by the way, I have provided links to all these data sheets, which are useful for you to think about. This is essentially plotting the primary energy consumption measured in terawatt hours. Now, of course, terawatts is 10 to the 12 watts, right? Let me see, giga. Yeah, 10 to the 9 is giga, so 10 to the 12 is tera. Here, there's efficiency factors included, so I'm going to skip all that. That's fine. So this is in terawatt hours, which is a unit of energy, right? Terawatts is power. Watt hours is energy. So terawatts is power. Hours is time, right? Power multiplied by time is joules, right? We know this. This is energy. So this is the total energy consumption, annual consumption per year. Okay. Obviously, it's been going up over time, and this is just showing the breakdown. So if we look way back here, it was mostly oil, a little bit less was coal, and then it was mostly other stuff like biofuels, which is what, as we talked about this before, most of the developing world works on, utilizes, and very small percentage was other stuff like wind, solar, other kinds of renewables and so on. Hydropower is actually was a big deal. It's still very important, of course. Now, if we fast forward to today, something like 50 years later, what we still have pretty significant amounts of oil, significant amounts of coal. However, biofuels, also a pretty significant amount of biofuels. By the way, that's primarily because of population increases. In fact, you can argue all of these are due to population increase, but also because of our consumption patterns have changed. Of course, we are flying more, we are driving more, so on, right? Fortunately, we have other renewables come into play here, things like nuclear, hydropower, and very small percentage of solar, wind, and so on. One way to see this is that there's a huge room for improvement. Another way to see it, of course, is that we really need to address this because of the issue of CO2 emissions. So now, what is the potential of photovoltaics? So we are using only a very small percentage of photovoltaics, but what is the potential? As we have seen before, the potential can be quite significant. The total solar flux reaching the Earth, if you average over the entire the cross-sectional surface area of the Earth, it's about 89,300 terawatts. That's a huge number, right? Obviously, we cannot capture all of this, and it is spread over a very large area. So this is a huge number, but the density is very low, right? In other words, it is spread over the entire Earth's surface. So to collect it is a really, really tough problem. This is the real big challenge in photovoltaics. Now, if you come back to the energy consumption, which we just talked about in the previous slide, it's only about 20 terawatts. So one could argue, of course, the sun is providing many orders of magnitude more energy, or power, I should say, than what we actually consume. So obviously that gives us some hope that we can actually try to match what we consume from solar. Of course, it's a difficult problem. If you assume something like 17% panel conversion efficiency, this means an extraction of 0.13% of the sunlight hitting the Earth would need to be harvested to meet global power demands. That seems like a very small number, but because the power density is so small, this translates into huge area. I don't want to go into the number of square miles, but a good rule of thumb, which I saw Harry Atwater at Caltech talk about, was basically if we take all the roads in the US and convert them to solar panels, the area convert them to solar panels, that would actually be enough to offset our entire consumption. So that's obviously a huge surface area, and it's not feasible to do that for obvious reasons. Now let's look at where things are in terms of global potential. So here, what we are seeing is a photovoltaic resource map across the Earth, and of course near the equator we have huge solar resources. As we go further away from the equator, the solar resources go down. We are in Utah. We are, of course, very fortunate to have huge, very, very favorable solar resources. Now, if you look at the daily total, so I should explain this unit. This is a very important unit, kilowatt hours per kilowatt peak. What does that mean? Kilowatt hours is the unit of energy. So that is the total energy either per day or per year that is produced from the solar panel, divided by the peak power produced by the solar panel. So that gives us an idea of how many hours, right? How many hours of useful sunlight, because peak power times the average hour gives me the energy. So there's a good measure of, okay, how quickly can I charge up my battery so I get so much power? Or how many hours do I really need? So as you go further away, so it's a from the equator. So it's a way to normalize the yield or the capacity of the solar panel to the location. If you look at the numbers, an average is about 5, which basically means on average it would take about 5 hours to get the equivalent of total peak power. over that 5 hours. Not exactly, but yearly total is about 1,800. And you can see the map, the numbers on this chart here, and this is kind of where we are in the average. This is also called the yield, okay, kilowatt hour per kilowatt peak. Of course, the higher the yield, the better. So more power, of course. It's also a measure of the efficiency of the system and so on, right? So some assumptions have to be made here. Now, I took the chart from a very recent Financial Times article. So it's a very interesting article, which I will put a link to in the website. So I strongly encourage you to read through it, because it is a economics analysis of what the future, at least in the next 10 years to 15 years, will bring in terms of wind and solar. So there's a huge prediction. There are many interesting predictions there, but important prediction is where wind and solar could lead the renewables charge, and the results are not nothing surprising here. But the map really follows the similar sort of map that you saw in the previous slide. The coincidence, of course, comes from the fact that the global irradiance corresponds to what I showed in the previous chart. Here, what's also interesting is that it is overlaid with the current oil and gas reserves. So, obviously the goal that we have in order to maintain the temperature rises is to ensure that the oil and gas reserves remain in the ground as opposed to being burned, hopefully in the next decade or so. The other things to keep in mind is that what are the top 10 countries for electricity generation from solar in terms of terawatt hours. Interestingly and importantly, China is the #1 producer. And this is important because China has the largest population in the world as well. So it is very critical that the vast more people move to solar, of course, the better for our planet. We are, of course, relatively close behind. And then interestingly, other countries like Japan and Germany, for historical and policy reasons, are also quite in the top 3 and 4. Even though, as you can see, Japan does not have a significant amount of insolation, nor does Germany out here, right, compared to other countries. But the reason they're the top 3 and 4 is because of very early on policy decisions that were made. If you've ever been to Japan or Germany, especially when you fly in, you can very, very clearly see the huge number of solar panels. For instance, if you fly into a place like Berlin or somewhere where the airport's actually in the city, you can actually see huge numbers of solar panels on the houses. And interestingly, Berlin is way up north, very, very little sunlight. So it's clearly driven by policy, for good or bad, but overall, hopefully for the future to be good. Of course, the other countries like India and Italy and UK, Spain, France, Australia, these are all very, very big players in the scheme of things. Many tens of terawatt hours of power per year. So quite large numbers here. Still, I mean, large in the absolute scale, but small in terms of the percentage of the total power generation. Okay, so what is the current global capacity of solar PV? That's what was installed, what actually is existing today. And I think that was 28. This article is actually from 2021, but the numbers are from 2020. Actually, these numbers are from 2018. This is what's actually installed today. What is the potential? Not what's installed. So here, the capacity is about 500 gigawatts. Again, this is power. And the previously was kilowatt hours, so that's energy. So it's good to think about these conversions between them. Clearly, there's a pretty exponential increase, as you can see. Again, the countries are broken down here, China and US being the major players. The other countries are relatively close behind. And most important numbers to keep in mind is 505 gigawatts of 0.505 terawatts. And the yearly totals we saw before, about 1,800, and electricity generation in the order of 1 kilo terawatt hour per year. So these are massive numbers, but again, a drop in the bucket in terms of our total consumption. Now, if we look at the contribution for electricity generation, this is a good graph because it breaks down the different modalities of electricity generation, similar to what you saw before. Coal, gas, and oil being the major producers. So this is where we are today, right? We're about here. So most of it is oil and coal. So I would say more than 50%, right? And the rest is nuclear, hydro, and a very small percentage is renewables. The prediction, of course, this is going to 2040 with different scenarios. Here you can see sustainable development and some sort of stated policies. If nothing changes, this is an important point that the FT article, actually the IEA article is making, is that if we don't do anything in the current state of things, we still have an increase. This is going to 2040, but it's still, we are keeping to less than 50% of the power. This is a big problem generally. If you ask most climate scientists, we really want something like a sustainable development where you want an even larger increase but a corresponding decrease. So you basically have more than 50% contribution from potential renewables, including nuclear, by the way, in this case. So this is a useful thing to keep in mind. And this is, of course, being negotiated as we speak today, this week, right? And there's also countries making commitments and so on. So, but this is the reason why we need to make this, why these meetings happen. So these numbers are also good to keep in mind. Some 37% is expected to be clean energy, like in the future, but of that, about 3.7% is solar. Okay, so a few other charts that we can appreciate coming now into the US. What is the capacity factor in the US? This is averaging 2014 to 2017 by state. The US average is about 25%. And of course, very nicely, Utah is way up here, right behind Arizona, almost neck and neck. And of course, this makes sense because this is per capita, by the way. So it makes sense because we have a huge amount of sunlight, right? So over 300 days of sunshine a year and relatively low population. So that's where that comes from. This is a more detailed metric in terms of watts per capita, which is the power generated. So it's actual power generated, not the capacity per person. And this is, we're in the top 7. Number 1 is Nevada. And the reason is because there's a couple of big utility scale power plants there. Then Hawaii. Hawaii is an interesting case study because that's where actually almost 10 years ago where grid parity was achieved for obvious reasons, because Hawaii doesn't have a significant amount of coal or oil power plants. California because of policy, and Arizona. Vermont is an interesting case. Won't talk much about it. I don't know much about it, but I'm pretty sure it's driven primarily by policy, because for those of you who've been to Vermont, you probably know that it's not that sunny there. But although it's a beautiful state, so nothing against Vermont. But Utah is pretty high up, so this is a good number to keep in mind. We're about 557 watts per capita, so it's relatively small in terms of population, but we are pretty heavy hitters in terms of solar. These are December 2020 numbers, so quite recent. There are over 7,000 jobs created by solar companies in Utah. This is a very nice map which shows where things are broken down. Of course, the vast majority of companies are based in the Wasatch Front and the Utah Valley. Of course, St. George is a big player as well because of the sunshine there. Relatively big number of installations, over 41,000, and almost 350,000 homes powered by solar. The percentage is slightly lower than the national average because we are a coal producing state, as you all know. About 8% of the state electricity is from solar, but this is increasing quite rapidly, in my opinion. Now, where are solar panels used? They're used everywhere, and just to give a sense, of course, calculators, a huge utility scale solar fields, And of course, we all know that the technical requirements between these two are quite dramatically different, right? So that gives you a huge diversity of possibilities of technologies there, and they exist. Of course, in space, it's very, very critical, especially for space exploration, but also for satellites, right? All our communications happens via satellites, so it's really important that they be powered, and all of them are powered by solar panels. Of course, residential systems are very important. Other standalone systems like parking meters or villages around the world, other homes. Of course, carports are becoming very popular, and other installations and so on. Interestingly, some lightweight solar systems are shown in these pictures. Of course, solar cars and things like that, which are becoming quite interesting. We also talked a little bit about these concentrated solar systems. I'll come back to this point later on in a different lecture, actually. In the interest of time, we won't talk about it. Of course, these are interesting applications as well. Okay, now, how do we think about the energy produced by a PV panel? So this is a picture of a cadmium telluride module, which is a thin film module. Okay, this is one module. Typically, it has an area of 2.47 meter squared. Sorry, this is a rectangle, so it has this width times the length. If you assume 1,000 watts per meter squared as the insolation from the sun, which is approximate, we talked quite a bit about this before. Typically, these numbers are about 1366 on the surface of the sun. We're going to assume 1,000. Area is 2.47 meters squared. An average efficiency is about 18.2%. These, as you probably know by now, it ranges anywhere from 10% to, I would say, the best in classes that you can buy commercially. Maybe it's like 22%, something like that. The peak installed power is 450 watts, which is simply multiplying these three things together, right? Insolation multiplied by the area, that gives the total kilowatts multiplied by the efficiency. And how much energy is produced? Let's imagine there are 5 hours of useful sunlight in a day, which is true in the summer. Might be a little bit more, of course, in the winter is a little bit less. So assuming 5, which is the yield number we talked about before, right? And then 5 times the 0.45 gives me about 2.25 kilowatt hours per day. This is, of course, not enough to power a home, but if you had about 10 to 20 of these kind of panels, that will be more than enough to power a modest, I would say, a reasonable sized home. Perhaps not a huge mansion. There are many technologies for PV out there, as you are probably familiar with, and this is a good way to think about them. The most dominant ones are silicon. So these are both silicon, okay, as the material. Now, they can come in monocrystalline form, which is basically the single crystal silicon. These are expensive, but more efficient. These are expensive because it's a little more difficult to fabricate them, manufacture them. They are made in wafers. The wafers are typically 6-inch or 12-inch in size, and they're diced out into these funny looking shapes. And then they are assembled, all of them together, into these panels. And you can see there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So it's 48 cells per panel, and that's kind of a standard. All of these are connected in series, typically, not always. Sometimes they can be connected in some combination of series in parallel. That's actually a very important design decision that is made by the manufacturers. The second type of material is polycrystalline silicon, which is a little bit cheaper, and they look bluer. And that's because it is reflecting some of the blue light. Of course, black is good, right? Because the black means that you're absorbing vast majority of the visible light. Blue means that you're reflecting the blue. So you're losing some of the very high energy photons. And that's not a big deal for polycrystalline silicon, because if you recall, the external quantum efficiency has a drop. If you remember from last week's lecture, the EQE drops at the shorter wavelengths. So you actually, in the case of polycrystalline, and this is about the blue. You don't worry too much about it. And this is a little bit cheaper because you can work with fragments of silicon, and they're typically diced into squares as shown here, and again assembled into 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So that's a standard there. Now, there are, of course, other technologies other than silicon. Cadmium telluride is the next most popular technology, I would say, is thin film. It has the advantage that, what does thin film mean? This means it uses less material. So silicon typically is maybe 300 microns thick, whereas cadmium telluride can be just 10 microns thick or less. So this is a reduction of a factor of 10x, right? Or more, 30x. So that saving that material reduces the cost. And of course, the cadmium telluride thin film materials can be processed in a cheaper manner using wet processing, wet chemistry, and so on. So this allows you to make them a little bit cheaper. Interestingly, they can also be made flexible. This is a different material. This is copper, indium, gallium selenide, I believe. I actually don't recall what this is. I don't remember if there's gallium in it. But in any case, they can be flexible, so they can be put on plastic, and of course that has many advantages for applications. You can also have amorphous silicon, which is not crystalline at all. So there's no crystalline structure. It's like glass. It also looks a little bit bluish. It's a little bit cheaper to make. In fact, if you look at the calculators and so on, this is what's typically used. In fact, almost all the solar panels used to be amorphous silicon until about 20 years ago, because it was too expensive to make the other kinds. And this is a good graphic to keep in mind where things stand in terms of technology. So here, the two buckets of technology. One is crystalline silicon, which vastly dominates the market today, and the other one is thin film PV. And then there are other buckets, which we will talk about shortly, but let's just concentrate on these two for now. So if you look at this chart here, this plots year. So in this vertical axis is year. And of course, it's expanding. This horizontal axis is modules, how many gigawatts, peak gigawatts. So it's essentially the total module production volume. And it's, of course, expanding like crazy, right? It's exponentially increasing. And this is showing the breakdown. So the polysilicon or multi-crystalline silicon, which includes amorphous, is shown there. Sorry, amorphous is in thin film, so that's not ignored. The monocrystalline silicon, which of course is dominating, as you can see. The monocrystalline silicon is dominating. And then because the efficiency here is good. And then the thin film is a much smaller portion of the market because the efficiency generally tends to be lower. What else to keep in mind? This breakdown here is also useful to think about in terms of what are the thin film technologies that are important. Cadmium telluride is dominating at 5.7 gigawatt peak, and then is CIGS, and then amorphous silicon. Cadmium telluride dominates because its efficiency is a little bit higher than the others. Now, what about the pricing? Because if the reason why a customer will install solar panels on their roof, really, most of us won't do it for altruistic reasons. We want to make sure we get some payback on our investment. So the module costs are very important. And fortunately, the module costs have come down like crazy. So this has been heuristically called something called Swanson's law. Where Swanson actually predicted this or he observed this from data similar to Moore's law, where the price of solar photovoltaic modules drop about 20% for every doubling of the cumulative shipped volume. So this is the module price in log scale, and this is the cumulative production in gigawatt peaks in log scale. So every doubling of this, you have a 20% drop. So it's essentially an exponential curve, but when you plot them in log, it becomes a linear curve, as shown right here. It's shown both for the crystalline silicon as well as for thin film technologies. And the price drop is pretty incredible if we really think about this. We are really witnessing history at this point because the numbers are so low. I would say the huge credit goes to the vast increase in production volumes in China, primarily, for good or for bad. The total cost, of course, includes not just the module, which is what we talk about primarily, but it also includes the inverters. We saw that cabling, mounting, labor, transportation, all this stuff. All this stuff is called balance of systems, BOS. And nowadays, it actually accounts for about 50% of the total cost. So if you are a homeowner and you try to install something like this, about half of your cost actually goes to all this stuff, balance of system stuff. Which is good and bad. I mean, we have squeezed a lot of pricing from the modules, but still lots of innovation waiting to happen on the other stuff. So a lot of opportunities out there. We can look at the system cost with respect to electricity generation rates. In other words, what is the consumption per month, and how much it depends also on how much area do you have for installing PV. In the case of a residence, it's limited by the roof area, right? So this is a very nice plot because it shows, first of all, the horizontal axis is dollars per watt DC. So it's not the peak, but it's average. But nevertheless, it's just a good measure. In fact, if you open up your electricity bill, monthly electricity bill, you will see a number like this, or sometimes like cents per kilowatt hour. I can't remember exactly what the numbers are, but typically it should be in that order, cents per kilowatt hour. But this is plotting different charts as a function of time. Okay, so obviously the costs are going down. That's expected, but they're going down at different rates. So this is residential PV. This is a commercial PV. So residential PV is much smaller than commercial PV. So obviously the costs are higher, right? So this is $7 here, this is $5 here. But 6.2 kilowatts is 200 kilowatts. So that's the difference. Utility scale is much larger. This is fixed tilt, which means that you're not tracking the sun. This is utility scale one-axis tracker. So it's a parabolic concentrator, which is tracking the sun in one axis. The other axis is fixed. That's the lowest. So the most important numbers are these 2018 numbers, the closest we have. Utility scale is about $1.13. Non-tracking system is about 106. Interestingly, you can see this is a little bit lower than this. And the reason is because of the tracking costs. We'll come back to the question of levelized cost of electricity shortly. So here the tracker costs actually dominate, which by the way is broken down. If you zoom in here, you can see the numbers broken down. The module costs are roughly the same, but the balance of systems cost, which includes all this other stuff. Inverter, other hardware, balance of system structure, electrical components, soft costs, labor, other things, regulatory costs and things like that. In the case of homeowners, it's still about twice as big, $2.70. And that's purely limited by the volume. Of course, in the case of tracking, you can get more power out, so that also helps a little bit. Now, as we all know, solar is the largest price drop of all renewable energy sources. So how do we quantify this? That's quantified by something called the levelized cost of energy. This is dollars per kilowatt hour or cents per kilowatt hour. This is plotted in 2019 numbers. This is of course, this means this is dollars, so that means it's 40 cents. So 2019 offshore wind is about 11 or 12 cents, where solar is about 8 cents, much smaller. Onshore wind is a little bit cheaper, hydro is a little bit cheaper. So this is where we are approximately. Now, levelized cost of energy is a very important number. This actually primarily comes from economics, but it's defined essentially as this equation here. It's the sum of the costs over the lifetime. So which includes not just the module cost, but maintenance costs and replacement parts, whatever, divided by the sum of electrical energy produced over the lifetime. So this is dollars, this is kilowatt hours, right? So it's dollars per kilowatt hour. And this is a very complicated thing to calculate generally, but there's lots of resources out there, particularly from the National Renewable Energy Labs. There's lots of tools to do these analysis. But this chart on the top is very, very illustrative of where we are and where we are going to some extent, because this plots the cost per megawatt hour. So instead of kilowatt hour, 1,000 kilowatt hours is a megawatt hour, right? So it's just normalized. So these numbers are multiplied by 1,000 times the numbers in the previous slide. So that's why it's much larger. But in any case, interestingly, if you look at 2020 numbers, wind and solar are actually the lowest. And of course, this depends on location. So this is a particular location. I don't recall exactly. So this is a very favorable location. Natural gas is quite low. Geothermal can be low depending on where you are. Coal is starting to go up, right? You can see the trend of the curve there. For a variety of reasons. It's harder to find new deposits. I mean, there's regulatory costs, all kinds of other things, pollution. Solar thermal is still pretty high.